Hello, my friend. Few things feel more ordinary than a calendar, and yet behind it lies one of the most astonishing stories in all of science and human culture. Long before clocks, apps, or printed calendars, human beings were already reading time in light, shadow, moonrise, and stars. There was a time when no one could turn a page to check the month, no one could glance at a clock, and no one could separate daily life from the movements of the heavens above. And somehow, out of that world, people learned to read the sky well enough to build order out of uncertainty. That slow discovery shaped the rise of farming, the organization of societies, and even the way we still measure time today. It is a story about the sky, but it is also a story about us. And if sleep has been difficult tonight, my friend, then you are exactly where you should be. Breathe out, get comfortable, and let's begin at the very start of timekeeping. Chapter 1. Before calendars, there was the sky. Few ideas are more fundamental or more quietly astonishing than this one. Long before humanity learned to write down dates, build clocks, or name the sciences, the sky was already teaching our species how time works. The modern world can make time feel artificial, as if it lives only inside screens, watches, and printed pages. But for most of human history, time was not something people checked. It was something they watched. It arrived in the light before sunrise, in the return of the moon, in the changing height of the sun, in the stars that came back to the same part of the horizon after long absences. Before there were calendars, there were repeating patterns, and above all there was the sky. That simple fact shaped survival, movement, memory, ritual, and eventually civilization itself. To understand why the sky became humanity's first calendar, it helps to begin with a basic truth about human life. People have always needed to know when, not just where food is or how to find water or which path leads home, but when the cold will deepen, when the rains may come, when animals begin to migrate, when a river is likely to flood, when it is safer to travel, and when stored food must last until the next season. Timekeeping was not a luxury invented by settled cities. It was a practical necessity long before cities existed. A group that could sense the larger rhythms of the world had an advantage over one that could not. Even a rough awareness of repeating time could make the difference between preparation and surprise. Early humans did not begin with a neat idea of a year or a month. They began with lived experience. A place that was green became dry. The nights grew longer. A familiar bird returned. The air changed. The angle of sunlight on rock or grass looked different than it had before. These were not abstract measurements. They were felt changes in the environment. Yet as human minds grew more observant and more capable of memory, those changes could be connected. A winter was not only a hardship in the present, it could become part of a pattern. A return of warmth was not merely relief, it could become expected. The world was not random, it repeated. And the largest, clearest, most reliable display of that repetition was overhead. The sky offered something no forest, river, or herd could offer in quite the same way. A vast set of cycles that were regular, visible, and shared by entire communities at once. Day followed night with remarkable steadiness because Earth turns. The moon changed shape in a repeating sequence because of its motion around Earth and the changing geometry of sunlight. The sun rose and set, but not always in exactly the same place on the horizon, because Earth travels around the sun with a tilted axis. The stars appeared to drift across the night, and over longer spans, different stars became visible in different seasons because our planet changes its position in space over the course of the year. Ancient people did not know the modern physics behind these patterns at first, but they did not need that physics in order to notice the order itself. Observation came before explanation. This point matters because calendars did not begin as inventions in the way a machine is invented. They began as recognitions. Human beings noticed that nature keeps count. The world contains cycles, whether we name them or not. Long before anyone drew up a formal system of months and days, people were already living inside repeating astronomical rhythms. In that sense, the first calendar was not carved in stone or painted on bark. It was the recurring behavior of the heavens. What later societies did was translate those observed patterns into social systems. They gave names to intervals, fixed rituals to certain times, built structures aligned with sunlight or stars, and eventually wrote rules that allowed communities to coordinate. But underneath all of that was a much older experience. Looking up and noticing that the sky returns to itself. For mobile hunter-gatherer communities, this kind of awareness would have been especially valuable. Their lives were tied closely to changing landscapes, animal movements, plant cycles, water availability, and weather conditions. The sky could not tell them everything, but it could provide a stable backdrop against which other changes made sense. If a certain bright star appeared just before dawn, around the same time each cycle of seasons, that appearance could become associated with a local event, such as a migration, a thaw, or the ripening of a useful plant. If the moon returned to a familiar phase after a familiar span of nights, that could help structure memory and expectation even without writing. Human beings are excellent pattern learners, and the sky offered patterns large enough to be seen by all, yet regular enough to be remembered across generations. There is another reason the sky became such a powerful guide. It is public. A printed calendar is a tool owned by individuals. A clock can be hidden in a pocket or mounted on a wall. But the sun, moon, and stars are visible to everyone who shares the same horizon and weather. That made timekeeping, in its earliest form, a communal experience. A whole group could watch where the sun rose. A whole group could see a thin crescent moon after sunset. A whole group could notice that a familiar star had returned to the pre-dawn sky. This public quality gave sky-based time a social strength. It was not just one person's guess. It was something that could be pointed to, remembered together, debated, taught, and woven into the shared life of a people. Of course, the sky did not solve every problem. Astronomical cycles do not fit together perfectly from a human point of view. The cycle of the moon does not divide evenly into the cycle of the seasons. The apparent daily motion of the sky is simple, but the longer motions of the sun and stars require patience and repeated observation. Clouds can hide the sky. Mountains can change the horizon. Knowledge can be lost if it is not passed on. So the early use of the sky as a calendar was probably approximate at first, more like a set of remembered signals than a strict mathematical system. But approximation was often enough to begin with. Precision came later. What mattered first was not exactness, it was reliability. People learned that the heavens could be trusted to repeat more faithfully than many events on Earth. This is one of the quiet turning points in the history of human thought. When people began to recognize recurring celestial patterns, they were doing something deeper than merely checking the weather. They were discovering that time could be organized. The future was not completely unknowable. It could not be controlled, but parts of it could be anticipated. That is a profound intellectual shift. It means the world is not only experienced moment by moment. It can be compared across many cycles. Memory becomes more powerful because it is tied to recurrence. Planning becomes more possible because change is not pure surprise. In a sense, astronomy began not with equations, but with trust in repetition. The sky taught human beings that nature has rhythm. That lesson may have changed human culture as much as any tool. Once groups could connect celestial signs with seasonal changes, they could begin to coordinate action at larger scales. This would eventually support planting schedules, ritual gatherings, long-distance travel, trade, navigation, monument building, and organized religious life. But even before those larger institutions, there was a simpler transformation. Looking at the sky trained attention. It rewarded patience. It taught that some truths become visible only over long spans. A single sunrise tells very little. Many sunrises, remembered and compared, reveal a pattern. A single moonrise is beautiful. Many moonrises tracked in sequence reveal a cycle. The earliest calendar was therefore not just a system outside the mind, it was also a habit of mind, observing, comparing, remembering, and expecting. So when we say that before calendars there was the sky, we are saying something both simple and deep. We are saying that the first framework for human time was not manufactured. It was observed. It was written in light and shadow, in motion and return, in the dependable cycling of celestial bodies above a turning earth. Long before formal astronomy, people were already practicing its oldest skill. Careful attention to recurring phenomena. They learned that time leaves signs. They learned that the heavens can act as a map of change. And from that patient watching, the idea of the calendar slowly emerged. As this chapter comes to rest, it is worth holding on to that image for a moment. A world with no screens, no clocks, no pages to turn, and still the great patterns of time unfolding overhead with silent consistency. The people below that sky were not cut off from time. They were immersed in it. And perhaps there is something calming in remembering that even now, beneath all the noise of modern life, the same sky still moves with that ancient steadiness. You do not have to organize the whole world tonight. For a little while, it is enough to let the mind grow quiet and remember that time was once read in moonlight, sunrise, and stars. Chapter 2. Why the Sky Repeats Itself. The sky can serve as a calendar only because it is not random. Night after night and season after season, the heavens seem to change, yet they do so in ways that return, repeat, and form patterns that human beings can learn. This is the central reason ancient sky watching became useful. People were not simply staring at beautiful lights overhead. They were seeing order. The order was not perfect from a human point of view, and not every pattern was obvious at once, but it was dependable enough that careful observers could begin to use it. To understand how the sky became a calendar, we first have to understand why it repeats itself at all. When people look upward, it is easy to imagine that the sky is moving around Earth. The sun rises in the east, crosses overhead, and sets in the west. The moon does something similar. The stars also seem to travel across the night from east to west. For most of human history, this is how the heavens appeared. An appearance was enough to start building practical knowledge. But the deeper reason behind this daily motion is Earth's rotation. Our planet spins steadily on its axis, and as it turns, different parts of the sky come into view. The result is the most basic rhythm of all: day and night. Because Earth rotates in the same direction each day, the sun appears to follow the same general path across the sky again and again. The same is true of the stars at night. If you were to watch the heavens carefully from one location, you would see that many stars rise, arc upward, and sink again below the horizon in regular ways. Some stars, depending on where you are on Earth, never seem to set at all. They circle around one point in the sky and remain visible through the entire year. These are called circumpolar stars. Their presence helped show ancient observers that the sky was not just full of scattered lights. It had structure. That structure becomes even clearer near the point around which the stars seem to turn. In the northern sky today, that direction lies close to the star, often called the North Star. It is not perfectly fixed forever, but over human timescales it appears nearly steady. Other stars seem to circle around it during the night. With patience, people could see that the heavens revolved in an organized way. This apparent turning gave the night sky a framework, and that framework made memory possible. The daily repetition, however, is only the beginning. If Earth only rotated and did nothing more, the sky would look exactly the same every night at the same time. But Earth also travels around the sun. As it moves along its yearly path, the nighttime side of the planet faces different directions into space. That is why the stars of one season are not the stars of another. A constellation that rises in the evening during one part of the year may be invisible at that same evening hour months later, not because it has vanished, but because Earth has changed position in its orbit. In other words, the night sky changes through the year because we are moving. This yearly motion is one of the most important facts behind sky-based timekeeping. A person who watches over many months notices that the sky is stable in a deeper way. It changes in a cycle. Certain stars appear before dawn only at certain times of year. Certain star patterns become prominent in the evening during one season and sink into the sun's glare during another. They disappear, then return. This returning quality is what makes them useful as markers. Ancient observers could link the reappearance of a bright star or familiar star group with recurring events on Earth. The sun itself also changes position over the year, and this is where the sky's repeating order becomes especially useful. Although the sun rises every morning and sets every evening, it does not rise in exactly the same place each day. Its path through the sky slowly shifts. At one part of the year it rises farther toward one side of the horizon, then day by day that rising point moves, reaches an extreme, reverses direction, and travels back. The height of the sun at midday also changes through the year. These shifts happen because Earth is not only orbiting the sun, but doing so with its axis tilted. That tilt is the reason seasons exist. Earth's tilt causes sunlight to strike different parts of the planet more directly at different times of year. When one hemisphere is tilted toward the sun, that hemisphere receives more direct sunlight and longer days. When it is tilted away, it receives less direct sunlight and shorter days. The result is the familiar sequence of seasonal change. What mattered to ancient observers was that this process produced visible signs. The sun climbed higher or lower, shadows shortened or lengthened, the rising and setting points shifted along the horizon. Daylight grew or shrank. The moon adds another layer of repetition, one more immediately visible than the yearly drift of the stars. Unlike the stars, which keep their patterns relative to one another, the moon changes shape night after night. It may appear as a thin crescent, then a wider crescent, then a bright full disk, then begin to shrink again. This pattern is not caused by Earth's shadow during ordinary phases. Instead, it happens because the moon orbits Earth, and as it does, we see different portions of its sunlit half. Half of the moon is always illuminated by the sun. What changes is our angle of view. Because this cycle is so visually striking and repeats in a relatively short span, it became one of the earliest natural clocks available to human beings. The moon is also different from the stars in another way. It moves noticeably against the background of stars from night to night. A star pattern may hold its shape for generations, but the moon wanders through the sky. So do the bright planets, which is why ancient observers often treated them as a special class of heavenly bodies. Their motion is more complex than the motion of the fixed stars because they too orbit the sun, and Earth observes them from a moving platform. For early timekeeping, the most important lesson was simple. Not everything in the sky repeats on the same schedule. Some cycles are daily, some are monthly, some are yearly. The sky is not one clock, but many clocks layered together. This layering is part of what made sky watching such a powerful intellectual exercise. To understand the heavens, observers had to separate different kinds of repetition. One cycle came from Earth's rotation and created the daily rising and setting of celestial bodies. Another came from the moon's orbit and created the changing lunar phases. Another came from Earth's journey around the sun and created the seasonal shift of stars and sunlight. These cycles overlap, and sometimes they can be confusing. Yet confusion did not make the sky useless. Once people began to distinguish one repeating pattern from another, the heavens became a readable system. Even the apparent irregularities of the sky often sit inside a deeper regularity. Clouds may hide the moon, weather may blur the stars, twilight changes with season and location. But above those temporary conditions, the larger astronomical cycles continue. The sun does not forget to return to its turning points. The moon does not stop circling Earth. The stars do not abandon their seasonal order. This reliability is one reason sky-based timekeeping could persist across generations. A community could pass down knowledge not because the sky looked identical every night, but because its changes themselves were lawful. There is also something important about the speed of these changes. The patterns of the sky unfold slowly enough to be observed by human beings without instruments, yet quickly enough to matter within a single lifetime. Day and night can be experienced immediately. Lunar phases become obvious within a short stretch of evenings. The yearly return of seasons can be remembered from one year to the next. This made the sky a uniquely suitable teacher. It was not too fast to follow and not too slow to notice. Human memory could hold it. In this sense, the sky repeats itself because Earth is a moving world in a moving system. Our planet rotates, orbits, and tilts. The moon circles Earth. The other visible planets follow their own paths around the sun. From the ground, these motions produce patterns that seem both dynamic and dependable. Ancient people did not begin with the full physical explanation, but they could still recognize the repeating results. They saw that the heavens were not a chaos of lights. They were a set of rhythms, and once rhythm can be recognized, time can begin to be tracked. That is why this chapter matters in the larger story. The sky did not become a calendar because humans wished it to. It became a calendar because nature itself provides recurring signals. Every sunrise, every returning crescent moon, every seasonally shifting star field was part of that signal. To watch the sky carefully was to discover that time leaves marks. The heavens were not only beautiful, they were measurable. And there is something reassuring in that thought. Beneath the complexity of life, the larger motions continue with quiet faithfulness. The turning earth still brings dawn and night. The tilted world still carries us through the long breathing of the seasons. The moon still waxes and wanes above us, just as it did for countless people before us. If the day has felt crowded or uncertain, it can be calming to remember that above all human noise, the sky is still keeping its ancient rhythm. Chapter 3. The Sun as Humanity's First Timekeeper. If there is one object in the sky that first taught human beings how to feel the passage of time, it was the sun. Long before written calendars, mechanical clocks, or formal observatories, sunlight itself gave people a way to divide life into meaningful parts. Morning was the return of light. Midday was the moment when the sun reached its greatest height. Evening was the slow lowering of brightness toward the horizon. The sun did not merely illuminate the world, it organized it. For ancient people, it was the most visible, most immediate, and most practical timekeeper available. The reason is simple. Unlike the stars, which emerge only at night, the sun dominates the sky in a way that no one can ignore. It shapes sleep and wakefulness, warmth and cold, visibility and darkness, movement and rest. Even without trying to study it, human beings live under its rhythm. But once people began paying closer attention, they could learn much more than the difference between day and night. They could notice where the sun rose, how high it climbed, how long shadows became, and when the daylight lingered or faded more quickly. These were clues to the larger structure of time. At the most basic level, the sun gave people the day. Each sunrise marked a beginning, each sunset an ending. That alone was powerful. A repeating cycle of light and darkness is the simplest natural division of time that humans can experience. Yet the daily path of the sun also allowed for a finer sense of time within the day itself. Early in the morning, the sun stood low and shadows stretched long. As the sun climbed, shadows shortened. Around midday, when the sun reached its highest point in the sky for that location, shadows became shortest. Then, as afternoon deepened, they lengthened again in the opposite direction. By watching light and shadow, people could estimate the progress of the day with surprising usefulness. This may sound obvious to us now, but it represented a major kind of knowledge. It meant that time could be read from the environment. A person did not need to guess how far the day had advanced. The sun showed it. A stick placed upright in the ground could turn this observation into something even clearer. As sunlight struck the stick, it cast a shadow whose direction and length changed through the day. That simple arrangement, known in later societies as a gnomon, was one of the earliest timekeeping devices. It did not create solar time, it revealed it. From this came one of the most important solar markers of all, local noon. Local noon does not mean the time printed on a modern clock. It means the moment when the sun reaches its highest point in the sky for a given place on a given day. At that moment, the shadow cast by an upright object reaches its shortest length. For ancient observers, this was especially useful because it was repeatable and easy to identify with practice. Once people recognized local noon, they had a stable anchor within the day. They could compare one day to another and notice how the sun's height changed over the year. This is where the sun became more than a daily clock. It also became a seasonal one. If you watch the sun's path over many months, you find that it rises and sets at different points along the horizon as the year passes. It also reaches different heights at midday. In one part of the year, the sun rises farther toward one side of the horizon, climbs higher, and remains above the horizon longer. In another part of the year, it rises farther toward the other side, follows a lower arc, and leaves the sky sooner. These changes are caused by Earth's axial tilt as it travels around the sun. Ancient people did not need the full modern explanation in order to benefit from the pattern. They only needed to notice that the sun's behavior itself was cyclical. This made the sun an extraordinary guide for survival. The changing height of the sun and the changing length of daylight are closely linked to the warming and cooling of the world. Longer, higher, brighter days tend to accompany warmer seasons. Shorter, lower, dimmer days tend to accompany colder ones. Even in regions where local weather varies greatly, the overall solar pattern gives a reliable framework for the year. Communities could therefore use the sun to anticipate broad seasonal transitions. A careful observer might not be able to predict every storm, but they could tell when the year was moving toward greater warmth or greater cold. Over time, people began to notice that the sun has turning points. The rising point on the horizon shifts gradually from day to day, then seems to pause, reverse, and move back. The same is true of its setting point. Likewise, its midday height grows for months, then stops increasing and begins to decrease. These turning points are what we call solstices. The word itself reflects the impression that the sun appears to stand still before changing direction. Between those extremes come the equinoxes, the times of year when day and night are nearly equal in length, and the sun rises close to due east and sets close to due west. Such moments would have been especially important once people began relating sky patterns to practical tasks like movement, gathering, and planting. The sun's seasonal motion also encouraged people to observe the horizon more carefully. If a community lived in a place with hills, rock formations, or other fixed landmarks, those landmarks could be used as reference points. People could remember that the sun rose near one notch in the hills at one time of year and near another at a different time. In flatter landscapes, they could create their own markers. A line of stones, a post, or the corner of a structure could help track where the sun appeared on significant days. In this way, the horizon itself became part of the calendar. One of the remarkable features of solar timekeeping is that it links short time and long time in a single object. The same sun that tells you whether it is early morning or late afternoon also tells you whether the year is moving toward summer or winter. A single day's observation can reveal the progress of light, while repeated observations over many months can reveal the shape of the year. This made the sun uniquely powerful compared with many other natural signs. But the sun governs the whole rhythm at once, from the daily cycle of brightness to the annual cycle of changing daylight. Yet solar timekeeping also has limits. The sun is excellent for marking the day and the broad progress of the year, but it does not naturally divide the year into small equal units the way lunar phases seem to do. You can tell that the sun is climbing higher week by week, but those changes can be subtle unless you measure them carefully. A cloudy horizon can hide sunrise and sunset positions. Mountains can distort what counts as the visible horizon. The exact moment of local noon depends on where you are. So while the sun gave humanity a strong overall framework for time, people often needed repeated observation and later built markers or instruments to use it more precisely. This need for precision led to some of the earliest forms of solar engineering. A simple upright pole could be used not only to tell the time of day, but also to compare shadow lengths across the year. When the sun stood highest, midday shadows became shortest. When it stood lower, they became longer. A carefully watched shadow could therefore carry information about the season. Over generations, this sort of observation could become highly refined. What began as a basic awareness of sunlight and darkness could develop into formal methods for tracking the sun's movement. There's another subtle point here. The sun did not just help humans measure external time. It also shaped internal life. Human bodies are deeply influenced by light. Patterns of sleep, wakefulness, alertness, and tiredness all respond to the cycle of daylight and darkness. Ancient people would not have described this in modern biological terms, but they lived it directly. Dawn stirred activity. Dusk invited slowing down. The sun therefore acted as both a cosmic clock and a biological one. Because of all this, the sun was likely humanity's first great instructor in regularity. It taught that the world could be watched carefully and that repeated observation could reveal dependable change. A rising point on the horizon was not random. A shadow's shortening was not accidental. The gradual lengthening of day was not a mystery beyond all understanding. These were signs of an ordered world. Once that order was trusted, societies could build more upon it. They could align homes, monuments, and rituals with solar events. They could connect the sun's motion with planting and harvest. They could organize labor, travel, and ceremony around its dependable returns. So when we call the sun humanity's first timekeeper, we are saying more than that it marked daylight. We are saying that it gave early people a visible system for reading both the day and the year. It taught them that time has shape. It moves through brightening and dimming, climbing and lowering, lengthening and shortening. And unlike a hidden mechanism, the sun performed this work in full view of the world. Every dawn repeated the lesson. Every noon sharpened it. Every season completed it. There's something deeply calming in that image. Before clocks began to tick and houses and devices began to flash the hour, sunlight was already moving quietly across stone, grass, and skin, keeping time without noise. Even now, the same old rhythm continues above us. The sun still rises, still arcs, still leans higher and lower with the year. And as the day settles around you, it can be soothing to remember that one of the oldest clocks in existence has never stopped. Chapter 4. The Moon and the Invention of Months. If the sun taught humanity how to feel the day and the year, the moon taught humanity how to count the middle distance of time. Its changes are so visible, so regular, and so easy to follow with the naked eye that it is difficult to imagine ancient people not noticing them. A person does not need instruments, writing, or advanced mathematics to see that the moon grows, becomes round, fades, and returns again. This repeating cycle is one of the clearest natural patterns in the sky, and for much of human history, it offered something the sun alone could not provide so easily: a short, obvious, recurring unit of time that could be watched from one night to the next. That is why the moon became so closely tied to the idea of the month. The moon is especially suited to this role because its changes are dramatic. The stars shift slowly with the seasons, and the sun's yearly motion requires patience to track. The moon, by contrast, looks different from one night to the next. Sometimes it appears as a thin crescent hanging low after sunset. Sometimes it becomes a bright half circle. Sometimes it swells into a full disk that rises as the sun sets and lights the landscape deep into the night. Then it begins to shrink again. This change is not subtle. It is a pattern that almost insists on being noticed. For people trying to understand how time repeats, the moon would have stood out as one of the most useful signs in the sky. To understand why the moon changes shape, we have to be careful about a common misunderstanding. The moon is not actually changing shape, and its phases are not caused by Earth's shadow except during the rare event of a lunar eclipse. The moon is a sphere, and sunlight always illuminates half of it. What changes is our point of view from Earth as the moon travels around our planet. At one point in its orbit, the sunlit half is mostly turned away from us, and the moon appears dark or nearly invisible. At another point, the sunlit half faces us more directly, and we see a full moon. Between those extremes, we see intermediate portions of the lit half, producing crescents, quarters, and gibbous phases. The pattern is a matter of geometry, light, and motion. This cycle repeats with remarkable consistency. The interval from one new moon to the next, or from one full moon to the next, is called the synodic month. On average, it lasts about 29.5 days. That half day turns out to matter a great deal for human calendars, because it means a lunar cycle does not fit neatly into a whole number of days. A calendar based on the moon, therefore, cannot simply assign every month the same length without drifting away from the actual phases. This is one reason many historical lunar calendars alternated between months of 29 and 30 days. They were trying to stay close to a cycle that is real, visible, and slightly inconvenient. There is also another important lunar period, and the difference between the two helps reveal how carefully ancient observers eventually had to think. If you measure how long the moon takes to complete one orbit around Earth relative to the stars, the answer is a little shorter than the phase cycle. But by the time the moon has gone once around Earth itself has moved farther along in its orbit around the sun. That means the moon must travel a bit farther before the same phase appears again. So the phase month is longer than the orbital month. Ancient people did not need to calculate this in modern terms at first, but the practical problem was still there. The moon is regular, yet not every kind of regularity in the moon matches every other kind. Even without that deeper explanation, the moon offered a natural clock that ordinary people could use. Unlike the sun, whose daily motion is continuous and often needs reference points like shadows or horizons for exact tracking, the moon comes with built-in visual stages. Its changing appearance acts like a sequence. A thin crescent belongs to one part of the cycle. A half moon belongs to another. A full moon marks a particularly memorable point because it is bright, obvious, and socially visible. Entire communities can notice it at once. That made the moon especially good for shared timekeeping. People could agree that a cycle had begun, reached its middle, or neared its end because the evidence was hanging above them in plain view. This is likely why the moon became so important in early calendrical thinking. A month is a convenient human interval. A day is too short for many kinds of planning, while a full year is too long for everyday coordination. The moon offers something in between. It provides a repeatable span long enough to organize travel, gatherings, waiting periods, trade rhythms, and ritual observances, yet short enough to remain vivid in memory. A person can watch one full cycle without needing exceptional patience. A group can mark the return of the crescent or the full moon and connect that return with action. In this way, the moon did not merely decorate the night. It offered a practical unit of social time. The phase cycle also shapes the experience of the night itself. A waxing crescent often appears after sunset, while a full moon rises near sunset and shines through the whole night. A waning moon is more often seen in the early morning sky. So the month was not just counted by shape. It was also felt through changing patterns of moonlight and darkness. Before artificial lighting, bright lunar nights could affect movement, gathering, travel, and work after sunset. That gave the moon's cycle practical importance in everyday life and made it easier to remember. Yet the moon also introduced one of the great difficulties in the history of timekeeping. The cycle of lunar phases is real and easy to observe, but it does not match the cycle of the seasons. 12 synodic months make a year that is shorter than the solar year by roughly 11 days. This means that if a community follows only the moon and does nothing to adjust, its months will drift through the seasons. A month once associated with spring will eventually fall in winter, then autumn, then summer, and only much later return again. For societies whose main concern was ritual timing tied to the moon itself, this might be acceptable. But for societies that also needed their calendar to remain aligned with planting, harvest, and seasonal weather, the mismatch created a serious challenge. This tension between the moon and the seasons shaped the development of many calendars. The moon is easier to see directly, but the sun and the seasons govern the larger agricultural year. So human societies often had to decide which truth mattered more, or how to combine both. Some calendars remained strongly lunar. Others became solar. Still others used a lunisolar approach, trying to preserve lunar months while adding occasional corrections so that the months would not wander too far from the seasons. In that sense, the moon helped invent months, but it also forced people to confront a deeper reality. Nature contains several overlapping cycles, and they do not fit together perfectly. That imperfection is one reason the history of calendars is so intellectually rich. It begins with something simple enough for any child to notice: the moon changes shape. But from that simple observation grows a remarkable problem. How do you turn a visible celestial cycle into a reliable social system? How do you preserve the beauty of lunar recurrence while keeping festivals, labor, and agriculture in step with the world on the ground? The answer was never purely astronomical. It required decision, tradition, authority, and sometimes compromise. Yet the moon remained central because it gave human beings one of their earliest and clearest examples of recurring counted time. The moon also encouraged a special kind of attention, because its cycle is neither too short nor too long. It invites repeated observation. A person can remember where the crescent stood a few nights ago and compare it with tonight. They can anticipate the coming full moon. They can notice that after the bright fullness comes a steady decline into darkness and then renewal. This visible return may help explain why lunar imagery became so deeply tied to ideas of repetition and renewal in many cultures. The moon does not simply repeat. It seems to fade away and come back. For a species learning to think in cycles, that lesson would have been powerful. So when we speak of the moon and the invention of months, we are speaking about more than bookkeeping. We are speaking about one of the first times human beings could take a clear celestial cycle and use it as a shared measure of passing time. The moon offered a countable span, visible stages, memorable brightness, and a rhythm close enough to daily life that ordinary people could follow it without specialized tools. It made time feel graspable. It placed a repeating unit overhead and asked to be noticed. And perhaps that is part of why the moon still feels so intimate even now. The sun rules the day with overwhelming power, but the moon feels nearer to human attention. It changes gently, returns faithfully, and teaches patience through repetition. As this chapter settles, you can imagine countless people before any written calendar looking upward into the night and finding, in that calm, changing light, a way to hold time in the mind. The month was not first a page to turn. It was a cycle of moonlight, darkness, and return. Chapter 5. Stars that announced the seasons. The stars became seasonal markers because they offered something the sun and moon could not give in quite the same way. A broad, slowly changing map of the year written across the night. To an ancient observer, the stars may have looked fixed and eternal, but over the course of months they revealed a subtle and powerful truth. The night sky in early spring is not the same as the night sky in midsummer. The stars that dominate the evening in autumn are not the same ones that stood high at that hour in winter. This meant that the stars could do more than decorate darkness. They could announce where a community stood within the year. And for people living close to the land, that was knowledge of real value. At first, this might seem strange, because the stars themselves are extremely far away and do not rearrange themselves from season to season in any noticeable way over a human lifetime. The familiar patterns within constellations remain almost unchanged for generations. What changes is our view of them at night. As Earth travels around the sun, the nighttime side of our planet faces different directions into space during different parts of the year. So a star group that is hidden in the sun's glare during one season may return to the night sky months later when Earth has moved to a new place in its orbit. This is the key reason the stars can act as a calendar. Their seasonal appearance is a result of our own changing position in space. This made the stars especially useful as long-range markers. The sun is excellent for following the day and sensing the broad movement of the year, and the moon is excellent for shorter repeating cycles. But the stars provide a kind of background framework for the seasons themselves. If a certain constellation rises in the east soon after sunset, only during one part of the year, then its appearance can become linked to recurring events on Earth. A community might come to associate that star pattern with the start of a rainy season, the migration of animals, the return of navigable seas, or the right time to prepare fields. The stars therefore became not just objects of wonder, but indicators of change in the world below. One especially important idea in ancient skywatching is the heliacal rising of a star. This happens when a star or star cluster becomes visible in the dawn sky shortly before sunrise, after having been hidden for a period in the sun's brightness. Because this first visible reappearance happens at roughly the same season each year, it can serve as a dependable signal. In several ancient cultures, The heliacal rising of bright stars was tied to practical seasonal events. One well-known case is the star Sirius, whose heliacal rising in ancient Egypt became associated with the flooding of the Nile. Other star groups, such as the Pleiades, were linked in various traditions to farming or seafaring seasons. The important point is not that every culture used the same stars, but that many societies discovered the same principle. Certain stars return at meaningful times. This use of stars required patience and careful memory. The first dawn reappearance of a star is not always easy to catch. It happens low in the sky, in brightening twilight, and the exact day can vary depending on local conditions, latitude, and horizon obstructions. Yet over many years, the pattern becomes clear enough to matter. A community does not need perfect precision in order to find a star useful. It is enough that the star returns within a familiar window and does so more reliably than many events on Earth. In this way, the stars offered a kind of quiet, seasonal confidence. They did not predict the future in a magical sense. They signaled repeating natural relationships that careful observers could learn. The usefulness of the stars also depends on where you live. Latitude changes the sky. Some constellations are visible only in the north, some only in the south, and some can be seen from a wide range of places. Near the poles, certain stars never set below the horizon and circle the sky constantly. These are circumpolar stars. In other places, those same stars may rise and set like ordinary stars, or may not be visible at all. This means that no single star calendar fits the whole planet. Different peoples would naturally build different seasonal knowledge from the same sky because they were looking from different locations. The heavens are universal, but the horizon is local. This local quality helps explain why so many cultures attach deep meaning to different constellations and bright stars. A star that is an important seasonal signal in one region may not matter in another. The Southern Cross, for example, has a strong guiding role in southern skies, while observers farther north built seasonal knowledge around other familiar star groups. The same physical sky could therefore produce a wide range of traditions without contradiction. People were responding to real astronomical patterns, but they interpreted and organized those patterns according to the needs of their own land, weather, economy, and movement through the year. In that sense, star calendars were both scientific and cultural. They were grounded in repeated observation, yet shaped by local life. Another reason the stars were so useful is that they preserve their internal patterns. The brightest constellations appear to move across the sky during the night, but the stars within them keep the same recognizable shapes. This stability makes memory easier. A person may not remember the exact height of a single isolated star, but they can remember the return of a striking pattern. Human beings are very good at recognizing shapes. Once a cluster or constellation becomes familiar, its seasonal return stands out strongly. This is one reason why constellations became such powerful carriers of timekeeping knowledge. They were not simply stories written onto the heavens after the fact. Their shapes helped ordinary observers store the sky in memory. Of course, the stars were never a perfect calendar by themselves. Cloud cover, haze, mountains, and changing twilight conditions can interfere with observation. Some stars are bright enough to be noticed easily, while others are too faint for reliable naked eye tracking except under dark skies. And over very long spans of time, the sky itself slowly shifts because Earth's rotational axis changes direction gradually, a process known as precession. This means that the stars associated with one seasonal marker in one era may not line up in exactly the same way thousands of years later. Yet on the scale of individual lives and many generations, the seasonal use of stars remains highly effective. Their changes are slow enough to seem stable, yet regular enough to guide communities year after year. There is also an important difference between stars and the more immediate signs of weather or plant life on Earth. Terrestrial signs can vary from year to year. A cold spring may delay flowering. Rain may come early or late. Animal movement can shift with local conditions. The stars, by contrast, are not responding to those surface variations. Their seasonal return reflects the larger motion of Earth in space. This gave them a special authority. They were not useful because they caused every event associated with them. They were useful because their appearance was a dependable marker against which more changeable earthly events could be judged. In that sense, the stars announced the season not by controlling it directly, but by reliably accompanying the planet's place in the yearly cycle. Once a culture begins linking stars to recurring activities, the sky becomes more than a backdrop. It becomes a schedule. A bright star low in the dawn may mean it is time to prepare boats. A familiar cluster returning to the evening sky may mean the season is turning. A constellation standing high after sunset may mark a period for gathering, storing, or travel. Over time, such observations can become formal knowledge, then tradition, then ritual. But beneath all of that lies something very simple and very scientific. Earth moves through space in a repeatable path, and that motion changes which stars are visible at night. Human beings noticed that fact long before they understood its full physical cause. So when we speak of stars that announce the seasons, we are talking about one of humanity's great acts of patient attention. People learned that the sky has layers of time within it. The sun marks the day and helps reveal the year. The moon marks the month, and the stars, with their shifting seasonal appearances, spread the larger map of the year across the darkness. They taught people that winter, spring, summer, and autumn are not only felt on the ground, they are written overhead in returning patterns of light. For many generations, that was enough to build expectation, memory, and rhythm into human life. There is something soothing in that old arrangement. Night after night, the stars seem calm and distant, yet over longer spans they quietly tell a story of return. A familiar pattern disappears into sunlight, then comes back months later, as if the sky itself were breathing. And perhaps that is why people trusted them so deeply. In a world where so much could change without warning, the stars offered a larger steadiness. They reminded those who watched carefully that the year has a shape and that even in darkness, time can still be read. Chapter 6. When agriculture began to depend on the sky. Farming changed humanity's relationship with time, because a field does not reward people for reacting only to the present. A hunting group can adjust quickly to movement, weather, and opportunity, but a farming community has to think ahead. Seeds must go into the ground before food exists. Water must be expected before it arrives. Labor must be organized long before harvest can be gathered. This meant that once agriculture began to spread, people needed more than a general feeling for changing seasons. They needed a more dependable sense of when the world was turning from one phase to another. The sky, which had already offered recurring patterns of day, month, and year, now became tied directly to survival in a new and demanding way. Agriculture did not begin in one single place and then simply spread everywhere else. It emerged independently in several regions of the world, under different conditions and with different plants. But in all of those cases, one fact remained constant. Successful farming depended on timing. A crop planted too early may be struck by cold, dryness, or flood. A crop planted too late may fail to mature before the season changes. Harvest delayed too long can be lost to weather, pests, or rot. In this way, agriculture turned the problem of time into a practical question of life, effort, storage, and risk. Watching the sky was no longer only a way to notice nature's order. It became a way to reduce uncertainty. This dependence was especially strong because agriculture works with cycles that are slow, vulnerable, and largely irreversible within a season. If a hunting group chooses one valley instead of another and finds little game, it may still move again. But if a farming community chooses the wrong time to plant, it may have no second chance that year. The field becomes a commitment. Soil must be prepared, seed saved from the previous harvest, tools maintained, and labor shared across many hands. By the time the crop is in the ground, much of the year's hope is already invested. A society living by cultivation therefore benefits enormously from reliable signals that the environment is entering the right window for sowing, irrigation, weeding, or harvest. The sky offered those signals because the broad seasonal structure of climate is driven by the changing relationship between Earth and the Sun. Earth's axis is tilted, and as the planet travels around the Sun, the amount and angle of sunlight received at a given place shift through the year. This affects temperature, day length, evaporation, and the growth of plants. Ancient farmers did not describe these processes in modern physical language, but they could observe their effects. The sun's path climbed higher or lower. Days lengthened or shortened. Certain stars returned to the dawn or evening sky. The larger point became clear through experience. Changes overhead were linked to changes in the land. This did not mean the sky controlled every local detail of weather. Rain might come early or late. A river might flood more weakly one year and more strongly the next. Winds could damage crops. Cold might linger, yet the sky still provided the most dependable large-scale framework available. It told farmers where they were in the annual cycle, even when local conditions varied somewhat around that larger pattern. In that sense, the heavens were not useful because they removed uncertainty altogether. They were useful because they gave people a stable reference in a world where many things remained variable. A careful observer could not command the season, but could avoid being entirely surprised by it. This shift mattered most when communities became settled enough to rely on planned cultivation rather than opportunistic gathering. Settled agriculture ties food supply to a specific landscape. Once people invest in fields, irrigation, storage, and domesticated crops, they cannot simply wander away whenever timing fails. They must understand the place they occupy. That includes its rains, soils, floods, and seasonal light. Over generations, this encourages accumulated observation. Families remember when planting succeeded and when it failed. Elders compare one season with earlier ones. The motions of the sun, moon, and stars become linked not to abstract curiosity, but to the practical memory of land. One of the clearest examples of this connection can be seen in river-based agriculture. In ancient Egypt, the yearly flooding of the Nile was so central to farming that the calendar itself came to reflect the agricultural rhythm of inundation, planting, and harvest. The flood spread water and fertile sediment across the floodplain, and when the waters retreated, crops could be sown into the moist ground. In such a system, knowing roughly when the flood was due mattered immensely. Egyptian timekeeping became closely tied both to the solar year and to celestial observation, including the seasonal reappearance of Sirius, because these sky patterns were associated with the returning flood on which agriculture depended. The calendar was not separate from farming. It was part of the way farming was made possible. Other agricultural societies relied less on river flooding and more on rainfall, but the basic logic remained similar. In regions where crops depend on seasonal rains, planting too soon can waste seed in dry soil, while planting too late can shorten the growing period so much that the crop never fully matures. In such places, knowledge of seasonal solar patterns, locally important stars, and long experience with the usual onset of wet and dry periods becomes invaluable. Even if no single sign is perfect, several recurring signals together can guide decisions. A society may watch for the increasing height of the sun, the return of a familiar star cluster, the first steady warming of the ground, and the behavior of local winds and clouds. Agriculture often grows out of exactly this kind of layered environmental attention. The need to align human labor with seasonal timing also changed the social meaning of the calendar. Once fields must be planted and harvested in coordinated windows, timekeeping becomes a shared necessity. It is no longer enough for one individual to have a private sense of the season. Families, villages, and eventually states benefit from acting together. Seed distribution, field preparation, irrigation work, animal use, storage planning, and harvest labor all become easier when people broadly agree on where they are in the agricultural year. The sky helps make such agreement possible because its signals are public. Sunrise, the length of daylight, the phase of the moon, and the return of seasonal stars are visible to the whole community. This does not mean early agricultural calendars were precise in the modern sense. At first, they were probably approximate, rooted in repeated observation rather than exact calculation. But approximation can still be powerful when it is better than guesswork. If farmers know that a certain star's dawn appearance usually comes near the preparation season, or that the sun reaches a familiar point on the horizon when certain tasks should begin, then they possess usable knowledge. Over time, that knowledge can be refined. Marks may be placed on the horizon, shadows may be compared at midday. The first crescent of a new lunar cycle may be watched more carefully. But the underlying purpose remains deeply practical: to coordinate human effort with the recurring behavior of the Earth system. Agriculture also gave celestial knowledge a new emotional weight. When food depends on timing, the sky becomes more than an object of wonder. It becomes part of the moral and psychological structure of life. A badly timed season can mean hunger. A well-timed one can mean security, stored grain, and the ability to survive the coming months. That is one reason calendars often became intertwined with ritual. Seasonal observances did not arise only from symbolic thinking. They were also attached to moments of genuine material importance. The first sowing, the first fruits, the beginning of flood, the turn toward harvest. These were not arbitrary points. They mattered because communities depended on getting them right. Near the end of the last ice age, as climates shifted and ecosystems reorganized, early agriculture emerged, under changing environmental conditions in several regions. This broader context matters because farming did not arise in a timeless world. It developed in climates that already had seasonal structure, and it succeeded where people learned to work with that structure rather than against it. Domesticated plants have growth cycles. They germinate, leaf, flower, and mature in response to temperature, water, and day length. So as agriculture deepened, human beings had to become students not only of plants, but of the celestial and climatic rhythms that shape plant life. In a very real sense, the calendar became an agricultural technology long before it was written down as one. By this stage in the story, the sky was no longer only a distant order overhead. It had become a partner in earthly work. The sun indicated the broad turning of the year. The moon offered a visible shorter cycle useful for counting time within it. The stars marked seasonal thresholds with quiet regularity. Farmers did not always need a perfectly measured calendar, but they needed enough recurring guidance to know when to prepare, when to sow, and when to gather. Agriculture gave urgency to those observations. It turned the reading of the sky into an economic skill, a survival skill, and eventually a civilizational one. And there's something deeply human in that dependence. To farm is to trust that the future can be met if one acts at the right time. It is a wager placed months in advance, made under open sky. The seed goes into darkness before the food exists. The labor comes before the result. Ancient farmers looked upward, not because the heavens were abstractly interesting, but because the sky helped answer one of the oldest and most practical questions a settled people can ask. When must we begin? Even now, that old relationship feels strangely calming. Beneath every modern calendar lies the same older truth, that the land responds to seasons, the seasons follow celestial rhythms, and human life has long learned to breathe in step with them. Chapter 7. Monuments built to measure the heavens. There comes a moment in the story of timekeeping when watching the sky is no longer enough, and people begin to build their observations into the landscape itself. That is one of the most remarkable steps in human history. A sunrise can be remembered. A shadow can be compared from one season to the next. A star can be watched returning to the dawn. But a monument does something more. It fixes attention. It turns memory into stone. It allows a community to stand in a chosen place, look in a chosen direction, and see the heavens arrive at the same meaningful point again and again. When human beings began building monuments that aligned with the sky, they were not simply making sacred places or impressive structures. They were creating physical instruments for marking time. This does not mean every ancient monument was a scientific observatory in the modern sense. That would be far too simple. Many such places also had ritual, social, funerary, or political importance. Some alignments may have been symbolic rather than practical. Some may still be debated by archaeologists. But in many cases, the evidence is strong enough to show that certain structures were deliberately related to the motions of the sun, and in some cases to other celestial cycles as well. These monuments reveal something important about early societies. They did not only notice repeating patterns in the sky, they began to build those patterns into architecture. The logic behind this is easy to understand. The sky is regular, but human memory is imperfect. Clouds hide the horizon. People disagree. A generation passes, and local knowledge can weaken. A fixed structure helps solve these problems. If a monument is aligned so that the rising sun shines through a passage on a particular day, or so that the setting sun appears at a certain point between stones, then the landscape itself becomes a durable reminder of celestial order. Knowledge no longer lives only in stories and habits. It becomes part of a place. A monument can also increase precision. Earlier skywatching could rely on rough observations, such as where the sun rose on the horizon or how long shadows seemed at midday. But when a narrow passage, a doorway, a standing stone, or a line of markers is placed carefully, it becomes easier to identify a significant moment. A beam of light entering an inner chamber is harder to misread than a general impression that the sun seems to be rising farther north or south. In this way, architecture can sharpen attention. It takes a broad natural signal and frames it. One of the best-known examples is Stonehenge in southern Britain. Its structure changed over a long period, but one of its most famous features is its relation to the solstices. The monument is aligned so that at the summer solstice, the sun rises in the direction of the heel stone, and at the winter solstice, the setting sun aligns in the opposite direction through the center of the stone arrangement. This does not prove that Stonehenge was only a solar calendar. It almost certainly held multiple meanings and functions over time. But the solstitial alignment is real and striking. It suggests that the builders considered the turning points of the solar year important enough to embed in one of the most monumental constructions of prehistoric Europe. What makes such an alignment meaningful is not only the visual effect, it is the timing. The solstices mark the extreme points of the sun's annual movement along the horizon. In the northern hemisphere, one solstice brings the longest day and shortest night, and the other the shortest day and longest night. These are natural turning points in the year. If a monument captures one or both of them, it gives a community a dramatic way to witness the cycle of time in a public setting. At Stonehenge, the monument seems to gather people and celestial motion into the same event. Time becomes something visible, collective, and memorable. Another powerful example is Newgrange in Ireland, a passage tomb built more than 5,000 years ago. Near the winter solstice, at sunrise, sunlight enters through a specially designed opening above the entrance, often called the roof box, and travels down the narrow passage to illuminate the inner chamber. The effect lasts only briefly, but that briefness is part of its power. It is not ordinary light entering an ordinary room. It is a carefully framed event tied to a particular time of year. Whatever other meanings Newgrange had as a tomb and ceremonial place, this winter solstice illumination shows a deep awareness of solar motion and a deliberate architectural response to it. Newgrange also reveals something important about the social side of such monuments. A structure like this takes planning, labor, and shared purpose. It is not the work of one solitary sky watcher. To build a passage that captures a short seasonal moment requires collective effort and accumulated observation. Someone had to notice the sun's behavior over years. Someone had to decide that this moment mattered. People then had to quarry, transport, and place stones accordingly. A sky-aligned monument is therefore more than astronomy. It is organized society acting on astronomical knowledge. In some cases, the connection between monument and calendar becomes even more explicit. Chanquillo, on the coast of Peru, is one of the clearest known examples of a built solar horizon calendar. The site includes a row of towers placed along a ridge in such a way that an observer standing at designated points can track the rising or setting sun along the horizon through the year. The changing solar position can be marked against the towers, allowing dates within the seasonal cycle to be identified. This is not merely a symbolic resemblance to celestial order. It is a genuine calendrical instrument built into the landscape. For that reason, Timekeeping is especially valuable for understanding how architecture could be used to define time throughout the annual cycle, not just at one dramatic turning point. Sites like Timekeeping help us see that ancient monument building was not always about single spectacular moments like a solstice beam of light. Sometimes it was about repeated observation across the entire year. A horizon marker system allows people to watch the sun gradually shift from one extreme to another, then back again. That kind of arrangement transforms the horizon into a measured scale. It does not replace the sky. It makes the sky easier to read. The monument becomes a tool for translating motion into knowledge. Mesoamerica offers another important lesson. Though here the story is more complicated and more scientifically interesting because it reminds us to be careful. Certain Maya architectural groups, often called E-groups, were once widely interpreted as straightforward observatories designed for watching solstice and equinox sunrises. Some examples do show meaningful orientations, and the broader Maya tradition clearly included sophisticated calendrical and astronomical knowledge. But more recent research has shown that the picture is not as simple as once believed. Many of these structures vary in orientation and may have marked agriculturally significant dates or carried symbolic importance, rather than serving as precise observatories in the narrow modern sense. This does not make them less fascinating. It makes them more human. Ancient architecture often joined practical observation, ritual meaning, and political power in the same place. That point matters because there is a temptation to look at every ancient alignment and imagine exact science everywhere. Sometimes the evidence supports strong astronomical intent. Sometimes it supports possible intent. Sometimes it shows that modern people have projected too much onto ancient structures. Good archaeology has to distinguish among these cases. A monument may be oriented toward the sun because that alignment had ceremonial meaning. It may have served as a public marker of season. It may have helped organize agricultural or ritual life, or it may do several of these things at once. The ancient world did not divide religion, politics, and astronomy in the same way modern institutions do. A place that marked the heavens could also be a place of burial, gathering, authority, and myth. Still, even with that caution, the larger conclusion remains strong. Across different parts of the world, people built structures that interacted intentionally with the movements of the sky. They created passages for sunlight, sight lines to horizon points, rows of markers, and ceremonial spaces oriented toward significant celestial events. These were not random acts of construction. They were expressions of a deepening relationship between society and recurring time. Once the sky had become a source of order, the next step was to make that order durable. There is also a powerful psychological shift here. A natural cycle is one thing, a monument is another. The sun will always reach its turning points whether humans notice or not. But when a community builds a monument to mark those moments, it declares that celestial time matters to human life. It says that the return of light, the turning of the year, and the measured passage of the seasons deserve a place in stone. The heavens are no longer only above, they are mirrored in architecture below. This may be one of the reasons such monuments still move people today. Even if we no longer depend on a solstice sunrise to know the season, we can still feel the force of a place designed around celestial recurrence. A chamber that fills with winter light, a ring of stones framing a sunrise, a line of towers tracking the year across the horizon. These are reminders that for much of history, time was not hidden inside a device. It was met in the world, in public, through attention and place. So when we speak of monuments built to measure the heavens, we are really speaking about a marriage between sky and society. People did not merely observe cycles, they anchored them. They set them into earth and stone so that the return of the sun could be witnessed, remembered, and shared. In that act, architecture became part of timekeeping. The land itself became a calendar, and there is something quietly comforting in that. Long before digital clocks and printed planners, human beings stood beneath open skies and built places that could hold a season in light. They trusted that the sun would return to the same edges of the horizon, that dawn would arrive through the same passage, that the year could be felt again in the same stones. Even now, those monuments seem to say the same thing in silence. The heavens move, the seasons turn, and time leaves traces that patient people can still see. Chapter 8. The Birth of Formal Calendars. At a certain point, watching the sky was no longer enough. A community could know that the sun had reached a turning point, that the moon had returned to a familiar phase, or that certain stars had come back to the dawn. But practical life demanded something more stable than memory alone. People needed a system that could be carried forward, taught clearly, and used to coordinate many lives at once. That is where the formal calendar begins. A formal calendar is not just a set of observations about nature. It is a structured agreement about how time will be counted, divided, named, corrected, and shared. It takes the repeating patterns of the heavens and turns them into an organized human framework. This was an extraordinary step in human thought. The sky presents cycles, but it does not present them in neat human units. The solar year does not divide itself naturally into equal whole number months, and the lunar cycle does not fit cleanly into the seasonal year. Nature gives patterns, but those patterns do not come prepackaged as a perfect social system. A formal calendar therefore requires translation. People must decide where a month begins, how long it lasts, when a year starts, and what to do when the visible motions of the heavens do not line up exactly with the needs of agriculture, religion, administration, or trade. In that sense, the calendar was one of humanity's earliest great acts of scientific simplification. It did not change the sky, it created rules for living with it. The earliest formal calendars often grew out of the moon because lunar phases are easy to observe. A new month could begin with the first visible appearance of the young crescent after conjunction, and the sequence of phases offered a visible structure that ordinary people could follow. In ancient Mesopotamia, calendars based on lunar months became highly influential. A year of 12 lunar months, however, falls short of the seasonal year by about 11 days. That difference may seem small at first, but over a few years it becomes impossible to ignore. If nothing is done, a month once associated with spring slides backward through winter and eventually into autumn and summer. Formal calendar making began in earnest when societies recognized that this drift had to be managed rather than merely noticed. One solution was intercalation, the insertion of an extra month from time to time. This is one of the most important ideas in the history of calendars because it shows the moment when societies began correcting nature with rule-based adjustments. In early Babylonian practice, such extra months were added when observers and officials judged that the calendar had slipped too far away from the agricultural year. At first, this was not always done according to a fixed long-term rule. It could be irregular, based on need or authority, but even that irregularity reveals progress. It means the calendar had become something consciously maintained. People were no longer just following the moon, they were governing the relationship between lunar months and solar seasons. Over time, calendar systems in several cultures became more systematic. Instead of relying only on ad hoc correction, societies worked out recurring schemes for keeping lunar months in step with the year of the seasons. This was the birth of the lunisolar calendar in a stronger, more formal sense. The principle was elegant, even if the practice could be complicated. Preserve the visible rhythm of lunar months, but insert extra time at intervals so that spring remains spring and harvest does not wander into the wrong season. Later tradition recognized that a cycle of 19 solar years is very close to a whole number of lunar months, which allowed a more regular pattern of intercalation. That kind of solution marks a real intellectual advance. It reflects repeated observation, numerical reasoning, and the willingness to build a durable rule from celestial behavior. A very different approach appeared in ancient Egypt, where a highly schematized civil calendar emerged. Instead of trying to follow the moon closely, Egyptian administrators used a year of 365 days, divided into 12 months of 30 days each, with 5 additional days added at the end. This system had enormous practical advantages. It was simple, regular, and easy to use for civil life. Every month could be treated as equal in structure, and the year could be counted without waiting for uncertain lunar visibility. But this elegance came with a cost. Because the true solar year is slightly longer than 365 days, the Egyptian civil calendar slowly drifted through the seasons over long spans of time. The system was useful precisely because it favored administrative order over perfect astronomical fidelity. This tension between astronomical accuracy and civic convenience is at the heart of formal calendars. A calendar is never simply a mirror of the sky. It is also a tool for organizing society. Once months have names, once years begin on an agreed date, once taxes, rituals, contracts, and labor obligations depend on the calendar, stability becomes almost as important as celestial truth. That is why formal calendars often combine observation with convention. Some dates are anchored to visible cycles, while others are preserved because society needs continuity. A formal calendar must be predictable enough that people can plan their lives around it. It therefore becomes a compromise between nature's irregular exactness and humanity's need for manageable order. The Roman world shows this struggle clearly. The early Roman calendar was complicated and at times poorly regulated. Political interference and irregular adjustments allowed it to drift badly out of alignment with the solar year. By the time Julius Caesar introduced reform, the Roman civic calendar had moved far away from the seasons it was supposed to represent. The Julian reform addressed this by abandoning any real pretense of a lunar basis and building a more straightforward solar calendar. The year was taken as 365 and 1/4 days, with an extra day added every 4th year. This was a major step because it replaced a troubled civic system with a cleaner rule meant to preserve long-term alignment with the sun. Even that was not the end of refinement. The Julian calendar was an impressive reform, but its year was still slightly too long compared with the tropical year, the cycle that keeps the seasons returning in the same order. That small annual error accumulated over centuries, slowly shifting calendar dates away from seasonal markers. The Gregorian reform later adjusted the leap year rule to reduce that drift. This matters not because this chapter is about modernity, but because it reveals the deeper truth about formal calendars. Once a society decides to make time rule-based, it inherits an ongoing problem of correction. The sky keeps moving with subtle exactness, and the human system must occasionally be revised if it is to remain faithful to the heavens. What makes the birth of formal calendars so important is that it changed time from something mainly observed into something administered. A person no longer had to look directly at the moon to know the month or at the horizon to estimate the year's turning. The calendar could now be carried in memory, recited by officials, inscribed on monuments, and eventually written in documents. Time became portable. It could travel beyond the moment of observation. That portability transformed civilization. Trade, law, ritual, government, and agriculture all become easier when a society shares a common framework of named intervals and agreed corrections. Formal calendars therefore represent one of the earliest technologies of coordination. They allowed many people to live according to the same rhythm, even when they were not all looking at the sky at once. Yet the formal calendar never fully cut itself loose from astronomy. However abstract and administrative a calendar becomes, its deepest purpose remains the same: to keep human life aligned in one way or another with recurring natural cycles. A month may be standardized, a leap day may be inserted by rule, and a new year may begin by convention. But the reason such systems matter is that people still live on a planet that turns, tilts, and orbits. Formal calendars are not a rejection of the sky. They are a way of preserving its order in human institutions. They make celestial rhythm legible in daily life. So when we speak of the birth of formal calendars, we are speaking about the moment human beings stopped relying on observation alone and began designing durable systems of time. They named months, fixed year lengths, inserted leap periods, and built rules to reconcile the moon, the sun, and the seasons as best they could. In doing so, they created something profoundly powerful, a shared agreement about when life happens. And there is something almost soothing in that achievement. Behind every date lies a very old human effort to make the vast rhythms of the heavens gentle enough to live by, steady enough to trust, and clear enough to carry from one generation into the next. Chapter 9: How the Sky Shaped Ritual, Power, and Daily Life. By the time formal calendars had appeared, the sky was doing more than helping people notice the seasons. It was helping organize society itself. Once a community can say not only that the year is turning, but exactly when a feast should begin, when taxes are due, when labor must be gathered, when a ruler should be crowned, or when a sacred fast must end, time becomes a form of structure. The sky had always offered recurring patterns, but now those patterns were being translated into public order. This is one of the most important changes in the entire story of calendars. Timekeeping was no longer only about survival or observation. It had become part of power, religion, and daily routine. This happened because calendars do more than measure time. They coordinate people. A shared calendar tells a whole community when to act together. That might mean sowing and harvest in agricultural societies, but it also means festivals, temple ceremonies, legal obligations, court sessions, market cycles, military campaigns, and civic labor. Once many people depend on the same timetable, whoever defines that timetable gains influence. The calendar becomes more than a practical tool. It becomes part of the machinery of civilization. Ritual is one of the clearest places where this influence can be seen. Religious life in many early societies was tied to repeated moments in the year. The return of spring, the first harvest, the beginning of the flood, the winter turning of the sun, the appearance of a new moon, or the completion of a sacred cycle. Such events mattered because they linked human life to larger patterns in nature. They gave shape to hope, gratitude, fear, memory, and community identity. A festival held at the wrong time would lose some of its meaning. A ritual intended to welcome the new season had to occur when that season truly arrived, or at least when the calendar declared it had arrived. This is one reason religious institutions often took a deep interest in astronomy and calendar keeping. Sacred time had to be protected. In many cultures, this gave priests, temple officials, or learned specialists an important role. If the beginning of a month depends on observing the first visible crescent of the moon, or if certain ceremonies depend on keeping the calendar aligned with the seasons, then communities need people who know how to watch, interpret, and announce. That knowledge carries authority. It does not mean ancient people were simply controlled through ignorance. Rather, it means that calendar expertise became socially valuable. Those who could interpret celestial cycles could help determine when the community would gather, sacrifice, fast, celebrate, travel, or rest. Knowledge of the sky became institutional knowledge. Power entered this picture because rulers benefited from controlling time as well. A king or state that can declare the official beginning of the year, regulate intercalation, assign feast days, or coordinate taxation through the calendar is doing something more than keeping records. It is shaping the rhythm of collective life. This is especially true in large agricultural states, where timing affects food supply, labor obligations, irrigation work, and storage. A central authority that manages the calendar can make distant regions follow the same civic pattern. In that sense, calendars help transform scattered local time into organized political time. This political dimension is easy to underestimate today because modern calendars feel neutral. But in many ancient societies, the calendar was not neutral at all. It reflected decisions about whose reckoning counted, which festivals mattered, which era was being measured, and what kind of celestial or civic order the state wished to emphasize. Even the naming of months can reveal cultural priorities. Some month names preserve agricultural tasks, others preserve religious associations, and others reflect political identities. A formal calendar tells people not only when they are, but also what sort of society they live in. The sky also shaped daily life more quietly and intimately than grand rituals and royal authority might suggest. Before artificial lighting transformed human experience, daylight and darkness imposed a much stronger structure on ordinary routines. People woke, worked, traveled, cooked, gathered, and rested according to light. The sun still governed the broad schedule of each day, but once calendars became formalized, daily life could be tied more precisely to named dates and expected intervals. People could prepare for an approaching market day, a festival, a tax deadline, or a communal labor obligation because time was no longer only felt. It was anticipated. This anticipation changed the psychology of everyday life. A person living entirely in response to immediate conditions experiences time differently from a person living within a shared calendar. The first responds to what is happening now. The second also responds to what is scheduled to happen next. The calendar creates expectation. It allows households to prepare food for an upcoming feast, merchants to plan travel, officials to summon labor, and communities to gather at the proper season. In this way, the sky's recurring patterns, once turned into formal time, entered kitchens, workshops, roads, and fields. They became part of the ordinary texture of living. The moon often played a special role in this daily rhythm because lunar visibility gave common people an immediate sign of time passing. Even where official calendars were maintained by states or religious specialists, ordinary people could still look upward and see whether the moon was new, waxing, full, or waning. That visibility helped connect public time with personal experience. The month was not only a rule on a tablet or decree, it was something present in the night sky. This helped calendars remain socially persuasive. They were not arbitrary inventions detached from nature. They were systems that still pointed back to visible recurring phenomena. At the same time, the gap between visible sky and official calendar could become a source of tension. Because lunar months and solar years do not fit perfectly, and because civil administration often prefers regularity, official timekeeping sometimes required corrections or conventions that were not obvious from casual observation alone. This gave institutions even more importance. A priesthood, court, or state bureaucracy could decide when an extra month would be added, when the new year would begin, or which day would count as the correct date for a ritual. The sky remained the ultimate background, but human authority increasingly mediated access to its meaning. In practical terms, this meant that power could be exercised through the right to interpret time. This helps explain why celestial events often carried symbolic force far beyond their physical causes. An eclipse, for example, is simply the result of one celestial body moving into the shadow or line of sight of another. But for societies whose political and religious life was tightly bound to the sky, such an event could feel like a message or warning. If the heavens were taken seriously as a framework for order, then unusual celestial events could appear to challenge that order. Rulers and ritual specialists often had strong reasons to respond publicly to such phenomena, not because the event changed its astronomical nature, but because society had already invested the sky with meaning. The connection between time and power can also be seen in labor systems. Once states or temple institutions became large enough, they needed to coordinate work beyond the household. Irrigation channels had to be cleared, storage facilities maintained, building projects organized, and tax grain collected. None of this could be managed effectively without a shared schedule. A calendar allowed labor to be summoned at the right moment and justified in the language of proper time. Seasonal work became not only necessary, but official. When the calendar says it is time to begin, the social force of timing increases. Markets and trade also benefited from this structure. In many societies, exchange did not happen only whenever individuals felt like gathering. It could be tied to recurring days or ritual cycles. A predictable rhythm makes commerce easier. Traders know when people will assemble. Buyers know when goods will be available. Regional exchange becomes more reliable when communities share some agreed sense of timing. In that way, the calendar helped create economic trust. People could plan movement and expectation because public time had become more stable. Even memory itself changed. A society without a formal calendar can still remember events, but it often remembers them in relation to seasons, rulers, floods, harvests, or generations. A formal calendar allows events to be placed into a more exact framework. This makes administration easier, but it also changes culture. Births, deaths, treaties, wars, dedications, and religious observances can now be anchored to a date. Over time, this creates a more layered sense of history. The calendar does not only organize the future, it organizes the past. Yet despite all this institutional power, the calendar never ceased to be connected to human feeling. Festivals tied to celestial cycles often marked relief, gratitude, mourning, renewal, or communal belonging. A new year was not only an administrative turnover. It could feel like a real threshold. A solstice feast could mark the return of light in a dark season. A harvest celebration could mark the easing of anxiety after months of labor. A new moon could mark beginning, restraint, cleansing, or gathering. The sky shaped these emotions because it gave them recurrence. Feelings that might otherwise remain private were placed into public time. This may be the deepest reason the sky shaped ritual, power, and daily life so strongly. It offered a rhythm that was larger than any individual, yet regular enough to enter individual experience. A ruler could claim authority through the calendar, but the sunrise still belonged to everyone. A priest could announce the sacred date, but the full moon still shone over the whole community. The power of timekeeping came from this joining of the cosmic and the ordinary. The heavens provided the recurring pattern. Society turned that pattern into law, ceremony, obligation, and routine. So by the time we reach this stage of the story, the sky is no longer merely a natural backdrop or even only a source of calendrical knowledge. It has become part of the architecture of human life. It tells people when to gather, when to work, when to celebrate, when to fear, when to remember, and when to begin again. The motions of the heavens are still physical events governed by astronomy, but their meaning now reaches deeply into culture and power. Time has become social, and perhaps that is why calendars feel so powerful even now. We still live by dates that tell us when to stop, when to meet, when to mark a holiday, when to remember a loss, or when to begin a new year. Our lives remain threaded by shared time. It may no longer feel as visibly tied to the moon above us or the solstice sun on the horizon, but the old structure is still there underneath. The sky once taught human beings how to live together in time, and some quiet part of that lesson still remains. As the day loosens its grip and the mind begins to settle, it can be comforting to remember that behind all our schedules and obligations lies a much older rhythm, one first learned by looking upward. Chapter 10. From Sky Calendars to Modern Timekeeping. Modern time can feel completely separated from the sky. It appears on phone screens, computer corners, train timetables, and digital watches so effortlessly that it is easy to forget where it all began. Yet beneath every modern schedule lies an older framework built from celestial motion. The year is still tied to Earth's journey around the sun. The day still comes from Earth's rotation. Even some of the most precise modern time systems still keep one eye on the heavens, because civil time is not meant to drift too far away from the world of sunrise, sunset, and noon. The tools have changed almost beyond recognition, but the deepest foundation has not. Modern timekeeping is, in many ways, the long refinement of the ancient sky calendar. One of the first major steps in this refinement was the move from direct sky watching to calculated time. In earlier societies, people could look at the sun, the moon, or the stars and judge roughly where they were in the cycle of day or year. But as cities grew, trade expanded, and institutions became more complex, rough observation was not always enough. People needed a way to count time even when clouds covered the sky, when buildings blocked the horizon, or when they needed the same schedule to be followed indoors or far from the place where an observation had been made. This demand encouraged the growth of clocks and written calendars, systems that could preserve the order of the heavens without requiring everyone to observe the heavens directly. For many centuries, however, even clock time remained closely tied to the sun. In each town, local noon was the moment when the sun reached its highest point in the sky. Because places at different longitudes experience local noon at different moments, nearby towns could have slightly different times. This was not a serious problem in a slower world. If travel was limited and communication was local, a difference of a few minutes from one town to the next mattered little. Time was still, in effect, local sky time. The daily schedule of a place belonged to its own meridian, its own noon, and its own relation to the sun. This arrangement became difficult only when technology began to outrun local custom. Rapid rail transport and telegraphic communication in the 19th century made it much harder for each town to keep its own independent solar time. Train schedules could become confusing or dangerous if every stop followed a slightly different clock. Long-distance commerce and administration also worked better when regions shared a standard. That is why standard time and time zones emerged. Instead of every place using its own exact local solar time, wider regions began to agree on a common civil time. This was a practical compromise. It sacrificed some direct connection to the exact local sun in exchange for coordination across larger spaces. Time zones still preserve a sky-based logic, even though they simplify it. Earth turns through a full circle in about 24 hours, so the planet can be divided conceptually into 24 broad bands of time. In an ideal geometric system, each zone would cover about 15 degrees of longitude. In reality, time zone boundaries often bend for political, economic, and geographic reasons, but the underlying principle remains astronomical. Noon no longer means that the sun is at its exact highest point in every town, yet civil time is still organized around Earth's rotation. Modern standard time therefore did not abandon the sky. It regularized the sky for the needs of a connected world. The calendar itself also continued to evolve in this same spirit. The Gregorian calendar, now the most widely used civil calendar in the world, is a solar calendar designed to keep dates aligned with the seasons. It did not appear because older people were foolish or careless. It appeared because even very good calendar systems can accumulate small errors over long spans. The earlier Julian calendar treated the year as slightly longer than the seasonal year actually is, And over centuries, that small mismatch shifted calendar dates away from the seasonal points they were meant to track. The Gregorian reform corrected this by adjusting the leap year rule. This shows that calendars remain living systems. They must occasionally be revised if they are to stay faithful to the sky. There is another refinement hidden inside modern clocks, one that most people never need to think about. The actual sun in the sky does not cross the meridian at perfectly equal intervals throughout the year. The length of the apparent solar day varies slightly because Earth's orbit is not a perfect circle and because Earth's axis is tilted. For practical timekeeping, societies therefore use mean solar time, which smooths these variations into an average day. This was a profound conceptual step. It meant that human beings were no longer simply reading the sun exactly as it appeared from one day to the next. They were constructing a more stable mathematical version of solar time, one better suited to regular clocks and shared schedules. Astronomers, meanwhile, continued to use other celestial time systems for specialized purposes. One of these is sidereal time, which is based on Earth's rotation relative to the distant stars rather than relative to the sun. Because Earth is moving around the sun while it rotates, a sidereal day is slightly shorter than a mean solar day. This matters in astronomy because the stars return to the same position in the sky on a sidereal schedule, not a solar one. Telescopes and observatories can therefore use sidereal time when they need to point toward the same star at the right moment. This is a reminder that even in the modern scientific world, different definitions of time still arise from different ways of relating Earth to the heavens. The greatest leap in precision came when timekeeping moved beyond astronomy as its primary standard and entered the atomic age. For most of history, the second, like the day and the year, was tied ultimately to celestial motion. But Earth's rotation is not perfectly steady. It can vary slightly over time, which matters for high-precision science and technology. Atomic clocks offered a solution because certain atoms produce extremely stable frequencies of radiation. By using those frequencies, scientists could define the second in a way that is precise, repeatable, and far more stable than the turning of the planet. This shift did not erase the sky from timekeeping. In fact, it created a new balance between atomic precision and astronomical meaning. Modern civil time is based on atomic clocks because they are far more stable than Earth's rotation. But civil time is also kept close to astronomical time, the time tied to Earth's actual turning, because human society still lives on a rotating planet. Noon should not slowly drift into the middle of the night over many centuries. To prevent that, occasional leap seconds have been added to keep atomic civil time close to Earth rotation time. This is one of the clearest surviving links between the oldest and newest forms of timekeeping. The most precise clocks humanity has ever built still make adjustments out of respect for the sky. This connection becomes even more striking when we remember how much of modern civilization depends on precise time. Navigation systems, communications networks, financial systems, scientific experiments, and electrical grids all require accurate timing. A world of satellites and digital synchronization might seem infinitely far removed from ancient people watching the horizon. Yet the chain between them has never truly been broken. The ancient problem was how to know when the season was turning. The modern problem may be how to coordinate signals across the planet within tiny fractions of a second. But both problems belong to the same long human effort to align life with regularity. At the same time, older sky-based forms of time have not disappeared from human culture. Many religious calendars still preserve lunar or lunisolar elements. Seasonal festivals remain tied, directly or indirectly, to ancient solar turning points. Even the language of ordinary life still carries traces of celestial time. We speak of months that began in lunar reckoning, years that depend on Earth's orbit, and days rooted in the planet's rotation. We celebrate New Year's, equinoxes, and harvest times with customs that descend from far older efforts to keep human life synchronized with the world above. Modern timekeeping may be more exact, but it is not historically detached from its origins. So the true story of modern time is not a story of replacing the sky. It is a story of making sky-based time more portable, more precise, and more widely shareable. First came direct observation of repeating celestial patterns. Then came formal calendars and timekeeping rules. Then came local clocks, standard time, time zones, refined solar reckoning, and finally atomic standards. Each step solved problems the previous step could not fully solve. Yet every step still rests on the same underlying reality. Earth turns, Earth orbits, and human life unfolds within those motions. Even when we no longer look up to check the hour, we are still living inside celestial time. And perhaps that is the quiet lesson at the end of this whole journey. The modern clock may seem cold and abstract compared with the sun on a horizon or the first crescent moon of a new month, but it is not alien to them. It is their descendant. Hidden inside every exact second and every carefully corrected calendar is the memory of people who once watched light move across stone, tracked the return of stars, and waited for the season to turn. The world has become faster, brighter, and more synchronized than they could have imagined. But time itself still comes to us from the same place it always did, from a moving earth beneath a patterned sky. And there is something calming in knowing that behind all our devices, the old heavens are still there, quietly keeping the deepest time of all. And now, my friend, our journey through the sky and the birth of time comes to a quiet end. I hope this slow voyage through ancient calendars, sunlight, moonlight, and stars helped your mind grow a little calmer. If you are still awake, you might enjoy another video and continue wandering gently through the science of the universe. But if sleep is finally close, then let yourself drift. Good night, my friend, and sweet dreams among the stars.